In today's class of mine, I'll be telling you about the different types of unit cells. Unit cells are of two types, primitive unit cell and centered unit cell. Primitive unit cells are those in which the constituent particles which make up the solid are present at the corners of a unit cell. एक यूनिट सेल के 8 कॉर्नर्स होते हैं और उन 8 कॉर्नर्स पर कंस्टिट्यूएंट पार्टिकल्स प्रेजेंट होते हैं in case of a primitive unit cell. A centered unit cell is such a unit cell in which one or more constituent particles are present at the positions in addition to those which are present at the corners of the unit cell. This means that there are 8 particles which are present at the corners of the unit cell और इनके अलावा एक या उससे ज़्यादा constituent particles present होते हैं किसी भी और साइट पे. Centered unit cells are of 3 types: body centered, face centered and end centered unit cells. Body centered unit cells are those unit cells in which, apart from those particles which are present at the corners of the unit cell, there is one particle in the body, in the center of the body of the unit cell. मतलब यूनिट सेल में वो 8 कॉर्नर्स होते हैं जिन पे पार्टिकल्स प्रेजेंट होते हैं. हर एक कॉर्नर पे एक पार्टिकल होता है, लेकिन इनके अलावा एक पार्टिकल यूनिट सेल के बिल्कुल बीच में पाया जाता है. फेस सेंटर्ड यूनिट सेल. A face centered unit cell is such a unit cell in which one particle is present in the center of each of the unit cell, apart from those which are present at the corners of the unit cell. मतलब यूनिट सेल के कॉर्नर्स पे वो 8 पार्टिकल्स तो हैं ही, लेकिन एक यूनिट सेल में 6 फेसेस होते हैं और उन 6 फेसेस के हर एक फेस के बीच में एक पार्टिकल प्रेजेंट होता है. The third type of centered unit cell is end-centered unit cell. In end-centered unit cell, apart from those particles which are present at the corners of the unit cell, there is one particle each in any one pair of the opposite faces of the unit cell. इसका मतलब है कि ऐसे सेल्स में यूनिट सेल के 8 कॉर्नर्स पे जो पार्टिकल्स प्रेजेंट होते हैं उनके अलावा किसी एक ऑपोजिट पेयर ऑफ फेसेस के बीच में एक पार्टिकल प्रेजेंट होगा. Dear students, today I'll be telling you about the number of atoms in a unit cell. A unit cell doesn't only consist of atoms. They may be molecules, ions or atoms. But for our ease we use the term atoms. We will be discussing here about the number of atoms in a primitive cubic unit cell, a body centered unit cell and a face centered unit cell. First we come to primitive cubic unit cell. Here we can see that a cube has 8 particles at the 8 corners. But it's not only a cube. There are many such unit cells which constitute to make up a solid. Every unit cell has 8 neighboring unit cells with which it is in contact. So the particles which are present at the corners of a unit cell contribute only 1/8 towards a particular unit cell. That is why the total number of particles for a primitive cubic unit cell is 8 into 1 by 8, that is equal to 1. That means a primitive cubic unit cell has only one atom in it. Now we move to body-centered unit cell. In a body-centered unit cell, the particles are present at the corners of the unit cell, and in addition to that, there is one particle which is present in the body, that means in the middle of the unit cell. The contribution of that body-centered particle towards a particular unit cell of which it is a member is 1. That means it wholly contributes to that particular unit cell of which it is a member or within which it lies. So the total number of particles in case of a body-centered unit cell is a sum of that particular particle which is present in the body of the unit cell and the contribution of the 8 particles which are present at the corners. So the contribution of the 8 particles which are at the corners of the unit cell is only 1 by 8 per atom per particle towards that unit cell. So the total number of particles in a BCC is equal to 8 into 1 by 8, that is the contribution of the particles which are present at the corners, and 1, which is the contribution of the body-centered particle. So it sums up to 2. That means a body-centered unit cell has 2 particles, 2 atoms, 2 molecules, 2 ions and all. The last one is a face-centered unit cell. A face-centered unit cell, as I had told in my last class, is such a unit cell in which the particles are present at the corners of the unit cell, like a primitive cubic unit cell, and in addition to that, at the center of every face, each face, there is a particle. So there are 6 faces and hence 6 particles. With the contribution of those particles, of every such particle which is present at the center of the face of a unit cell is only half. So those 6 particles contribute, those 6 particles which are present at the faces, at the centers of the faces of the cubic unit of the unit cell is 6 into half, that makes it 3. And the contribution of those 8 particles which are present at the corners is equal to 8 into 1 by 8, and that makes it 1. So the total number of particles which are present in a face-centered unit cell is equal to 4. So if we compare all these 3 unit cells, we see that in case of the face-centered unit cell, the number of particles are more in a given space, in a given region, and that is why the packing here is more efficient. That means very little empty space is found in a face-centered unit cell. Thank you. Dear students, today I'll be telling you about close-packed structures. In solids, the constituent particles are closely packed, which means they leave very little space between them. And close packing can be done either in 1 dimension or in 2 dimensions or in 3 dimensions. At first we move to close packing in 1 dimension. The constituent particles in 1 dimension can be arranged only in one manner, and that is when the spheres are all arranged in a row. And in such type of an arrangement, leaving out the terminal particles, rest of the particles, each of them are in direct contact with 2 other particles. The number of particles which are in direct contact with the given particle is known as the coordination number for that particular structure. And so, the coordination number for close packing in one dimension is 2. Now we move to close packing in 2 dimensions. Two-dimensional close packed structures can be obtained by stacking the rows of the close packed spheres in one dimension. And this can be done in 2 different manners. The first one, you can see it's an AAAA type of close packing. In this case, in this arrangement, each sphere is in direct contact with 4 other spheres, 4 neighboring spheres. Now, how is this arrangement done? The arrangement is done in such a way that the spheres of the second row are exactly above the spheres of the first row. And so, the arrangement results in every particle to have 4 neighboring particles with which it's in direct contact. So, the coordination number is 4 in this case. Now, if we join the centers of those neighboring particles, we get the shape of a square. So, because of this particular shape, we call this type of close packing as close packing in 2 dimensions. Close packing in 2 dimensions can be obtained in another way. That's a B1, which you can see it's an AB type of arrangement. The arrangement is such here that the layers of the first layer and the third layer, that's the alternative layers, are similar. In this case, the close packed spheres of one dimension are kept above the spheres, close packed spheres in one dimension of another layer in such a way that the spheres of one layer are fitted in the depressions which are made by the spheres of the first layer. And because of this, if you consider any particular particle, you'll see that it is in direct contact with 6 other particles. 2 particles above, 2 particles on its own row, 2 particles in the layer below it, and 2 particles in the layer above it. So the coordination number in this case, in this type of close packed structure, is 6. Now if we join the centers of those neighboring particles, we get the shape of a hexagon. And because of this shape, this type of 2-dimensional close packed structure is known as hexagonal close packing in 2 dimensions. In this case, you get some voids, and those voids are triangular in shape. What are voids? Voids are the gaps, the empty spaces which are there between the various layers which are made up by the spheres. In between the spheres there are some gaps, and those gaps are known as voids. The voids here are triangular in shape. In one row, the apex of the triangle points downwards, and in the next row, the apex of the triangles point upwards. So we saw that close packing in 2 dimensions can be of 2 types. From there, we move to close packing in 3 dimensions. In case of close packing in 3 dimensions, the 2-dimensional close packed layers are stacked. one above the other. Close packing in 3 dimensions can be made in 2 ways, can be obtained in 2 ways. Most of all the solids, they have the 3-dimensional close packing structure, and they can be obtained, what I told you, is by stacking 2-dimensional layers one above the other. Close packing in 3 dimensions can be of 2 types. Basically, it can be of 2 types. Here we will be discussing the first type, and in my next video, you'll be seeing the other type. So in this type of close packing in 3 dimensions, the second layer is placed over the first layer in such a way that the spheres of the upper layer are exactly above those of the first layer. That is, the AAA type of close packing in 2-dimensional structure is repeated here. And this results in the formation of a cubical structure. So, because of this cubical structure, this type of lattice is known as simple cubic lattice in 3 dimensions, and its unit is known as primitive cubic unit cell. The next type of close packing in 3 dimensions, where it is made by stacking the AB type of layers one above the other, that is hexagonal close packed structures one above the other, can be seen in my next video. Thank you. Dear students, this is the continued class on close packed structures. This is the second type of close packing in 3 dimensions. In this particular type, one layer of AB type of 2-dimensional close packing is stacked over the other AB type of close packed structure in such a way that the spheres of the second layer lie in the depressions of the first layer. In this type of close packing in 3 dimensions, 2 different types of voids are formed. Voids are empty spaces when spherical structures, spherical atoms or particles, in general as we can say them, are closely packed. So the 2 types of voids which are formed are octahedral and tetrahedral voids. Tetrahedral voids are smaller in size than the octahedral voids. In this figure, which you can see, the red color spheres indicate the first layer and the green ones indicate the second layer. The tetrahedral voids can be distinguished from the octahedral voids. The tetrahedral voids appear to be triangular in shape, and the octahedral voids appear star-like in this figure. The spheres, the red ones or the green ones, they actually make up the lattice. The number of spheres which make up the lattice is equal to the number of octahedral voids which are formed. Let the number of spheres which make up the lattice be capital B represented by capital N. Then the number of octahedral voids will also be represented by capital N. As I told you, the tetrahedral voids are smaller than the octahedral voids. They are also double in number than the octahedral voids. So the number of tetrahedral voids in a lattice is given by 2n. Now, It may so happen that if a third layer is placed over the second layer in close packing in three-dimensional lattice, then two different cases may arise. The first case is if the spheres of the third layer exactly cover the tetrahedral voids, then the packing is known as hexagonal close packing structure, or it can be abbreviated as HCP. Some metals like magnesium and zinc, they crystallize in hexagonal close packing structure. The other case may arise when the spheres of the third layer cover the octahedral voids of the second layer. So if it happens, then this type of a lattice is known as cubic close packed lattice or face centered cubic lattice. So we abbreviate them as CCP or FCC. Few metals like copper and silver crystallize in CCP or FCC type of lattice. The coordination number in case of HCP and FCC lattices is 12. This means that one atom, any atom, in case of these type of lattices are in direct contact with 12 other spheres, 12 other particles. So the coordination number stands to be 12. In these two types of close packed structures, the packing efficiency is very high. This means that the spaces, the empty spaces which are there in these type of lattices is very less. Hello students, today I'll be telling you how to generate the formula of a compound. In order to generate the formula of a compound, we have to keep the following things in mind. The first one is, in case of a CCP or an FCC and an HCP structure, both the octahedral voids and tetrahedral voids are generated. The number of octahedral voids is equal to the number of close packed particles in the lattice, that is the particles which make up the lattice, and let us say that number is n. The tetrahedral voids are more in number, they are greater in number, that is because the tetrahedral voids are smaller in size. The number of tetrahedral voids, as I had told in my last class, is double the number of octahedral voids. And since the number of octahedral voids and the number of close packed particles are equal, so the number of tetrahedral voids is double the number of close packed particles. And that can be represented as 2n. In case of an ionic solid, the anions, which are bigger in size, make up the close packed structure. That is, those anionic spheres, they make up the lattice. And the cations, which are smaller in size, occupy the voids. If in an ionic solid there are two different cations, then the larger cations will occupy the octahedral voids, and the smaller sized cations will occupy the tetrahedral voids, because the tetrahedral voids are smaller in size than the octahedral voids. It's not necessary that all the voids be occupied. They may be occupied or they may not be. So the occupancy of the voids depends on the molecular formula of the compound. So we can say that the fraction of occupied voids depend on the chemical formula of the compound. To understand these particular things and how to generate the formula of a compound, I have written 2 examples. So let us go to the first example. The first example, it's a question in which we have to find out the formula of a compound which comprises of 2 elements A and B, in which the element B forms the lattice structure. It forms the HCP lattice, and the element A occupies 2/3 of the octahedral voids. We know that the number of octahedral voids is equal to the number of close packed particles, and we can represent both by n. Since only 2/3 of the octahedral voids are occupied, we can write A is to B. A, which occupies 2/3 of the octahedral voids, we can write it as 2/3n, and B can be written as n because it is the number of close packed particles which are represented by n. So, in order to generate the formula, we can write it as A is to B is equal to 2/3n is to n, which gives the value of A is to B as 2 is to 3. Hence, the formula of the chemical formula of the compound will be A2B3. We move to the second example, in which we have to generate the formula of a compound which comprises of 2 elements, X and Y. The element Y forms the CCP lattice, and the element X occupies only 1/3 of the tetrahedral voids. So, in order to generate the chemical formula of this compound, we have to write it as X is to Y is equal to 1/4 into 2n is to n. We have written X as 1/4 into 2n because 2n is the total number of tetrahedral voids, and 1/4 of them are occupied. So, it becomes X is to Y is equal to 1/4 into 2n is to n, which gives us X is to Y equal to 1 is to 2. So, the chemical formula of the compound becomes XY2. Similarly, you can try examples where you have 2 different cations and 1 anion, like A, B, C, and so on. While writing the formula, we need to keep in mind that the element which forms the lattice should be written at the last, and the elements which are occupied in the voids are to be written at first. Thank you.